We'll be working with acid-base titration, and the first part of this question is going to be balance the equation. So in this case, we have 2 hydrogens on the right, and we have 3 hydrogens on the left. So the easiest way is going to be putting a 2 in front of the hydrochloric acid. And we now have 4 hydrogens and 2 oxygens, so all we need is a 2 in front of the H2O, which will give us 4 hydrogen and 2 oxygens. Now the second part to this question is asking how much was needed to neutralize the hydrochloric acid. It wants to know the concentration of, so we're finding the concentration of the hydrochloric acid. And what we're given is 20 mLs of 0.25 molarity of the calcium hydroxide, which is going to be that OH2. Right? So this is what we're working with. So far we have the liters, we have the molarity, and we want to get to the HCl molarity. So in this equation, we're going to be using the coefficients in the moles to figure out the stoichiometry, and we're going to be using cross-dimensional analysis in this as well. So we're going to start with what we're given. So when we're working with molarity, we're looking at moles per liter. Okay? So in this case, we have 20.8 mLs. mLs of the CaOH2. And we want to convert this to liters. So we know 1,000 mLs is equivalent to 1 liter. And then we can use some of the cross-dimensional analysis to cancel out some of these units. So we know 1 liter is equivalent to lets me do it, 0.250 moles of CaOH2. Okay. So now that we have that, what else can we use? Well, we can go into moles. So we want to cancel this out. So this will be moles of the CaOH2. And we have the moles of the HCl. That's what we want to find, right? We want to find the HCl. So in this case, we have 2 moles of the HCl, and we have 1 mole of the CaOH2. So once we have all this, right, we can calculate it out, and this will give us 0.0104 moles of the HCl. So now that we have the moles of the HCl, we can then find the molarity of the HCl. We're already given the 15.0 mLs, and we've now found the moles. So we have everything we need. It's a plug and play. but remember that the mLs has to be in liters. So real quick, 15.0 mLs, 1000 mLs, 1 liter, equal 0.015 liters, and then we plug it in, right? 0.0104 moles of HCl. Let me write that better. HCl over 0.015 liters. And this will give us 0.693 molarity or concentration of the HCl acid. Alright, so that question's done. That's the answer. We'll be now moving on to the next one. And then, I can't ever say this name. This is the Lee Chantilly's principle. Oh my gosh, please be nice to me. Alright, so in this equation, we're looking at a few things, right? First, we're going to figure out what's our products and what's our reactants. This is going to be our reactants. And then we have our products. Now, there's another part to this where we have the heat. And we have to distinguish if this is going to be exo or endothermic. Endothermic is in the reactants, while there's heat is in the product side. This will be a exothermic reaction, right? We're given off heat as a byproduct. Okay, so now we have that, we can look at the KEQ expression, right? And that's products over reactants. This includes aqueous and gases. So now that we have that, we have the KEQ. So then I'm going to start with the products first. I'll just write them first. So we can see that H2O is a liquid. We will not be using that. So we'll be starting with the SO2 because it's a gas. There's no coefficients in the front, so no exponents. And then we have the NaI. NaI. And it has a 2 coefficient, so we'll be putting 2 on top. So that's it for the products. We will now be doing the reactants. Both are aqueous. So on the bottom, we're going to have the Na2SO3. Right? And it has no exponent, so we don't have, or no coefficient, so we don't need an exponent. And then we have HI. And it has a 2 coefficient, so we'll be putting a 2 on top. And that's the KEQ expression. Now moving down to the disturbances and shifts, we can see that because we're in an exothermic reaction and we're decreasing pressure, we're going to be going to the least amount of moles, or the most amount of moles. So when we're looking at this, we can see that we have one mole, 2 moles, we have 1 mole, 1 mole, we have 2 moles. So in this case, right, reactants has 3, and products has 4 moles. So we will be having a right-sided shift. And then now for the next part, we are increasing temperature. And because we're an exothermic reaction, we will have a left-sided shift. And then now when we add AI, we are adding more product. So if we can look at the little balance here, right, we are adding more product. So we're going to be shifting to the left to balance out. So this will be a left shift. And then with H2O, H2O is not part of the disturbance because it's not part of the EQ expression. So this will have no shift. Now if we remove the SO2, right, we remove the SO2, we now have more on the left side, so we will be shifting to the right in this case. So this will be a right shift. Alright, this wraps us up for the written responses. I'm not going to do the nuclear decay. I think everybody's pretty much gotten that one down. That one's pretty easy. So, yeah, that'll be it.